Hello students, today we will discuss Teitze extension theorem. Teitze extension theorem. This theorem tells us under what condition a function defined on a subset A of a topological space can be extended to a continuous function defined on whole space. This is the beauty of this theorem. Now the statement of this theorem is, let Xt be a topological space, T be a topological space. A topological space Xt is normal if and only if every continuous mapping F defined on A, where A is a closed subset defined on A, where A is a closed subset of X, extends to a continuous function F defined on whole space, that is value of F at A is equal to value of F at A. Xt is a topological space. A topological space Xt is normal if and only if every continuous mapping or function defined on A, F from A to where A B is a closed intervals, A is a closed subset of X, extends to a continuous function F defined on X. This is the Teitze extension theorem. Now, first we prove F from A to B is a continuous mapping defined on a closed subset A of X and it extends to a function F. Then we show that Xt is normal. Now, we come to the proof. Let F be a mapping defined on a closed subset A of a topological space, and that be a continuous map, and F extends to F on whole space. Here is closed subset of X, that is value of F at A is equal to value of F at A. This is given. Now show Xt is normal. Now we show Xt is normal. A topological space Xt is said to be normal if and only if for every pair of disjoint closed subset A and B of X there exist two disjoint open sets. Let A and B be two disjoint closed subsets of X. Define a map F from A union B to A B closed interval such that F of X is A if X belongs to A, and B if X belongs to B. Now we show F is continuous on the subspace A union B. To show F is continuous on the subspace A union B, we take a closed subset H of AB and find its inverse image under the continuous map F. Let H be a closed subset of AB. Now F inverse H. Now this is AB. A is less than B. Now this is H. Calculate this. If A belongs to H, B does not belong to H. By using the definition, it will be A. If A belongs to H and B does not belong to H, and it will be B if B belong to H, A does not belong to H, if B belong to H and A does not belong to H, it does not belong to H, and it will be A union B if A belong to H and B belong to H, and it will be phi if neither A belong to H and neither B belongs to H. This will be the F inverse H. Now we have taken A and B are a closed subset of X. Now A union B intersection A is A union B intersection B is B, A union B and phi. This A, B, A union B and phi are all closed subset with respect to subspace A union B with related to topology. Now A, B, A union B, phi are closed subset with respect to subspace A union B with related to topology. Related to topology. Therefore, inverse image of every closed subset, say every closed subset of AB is closed under inverse image of F. Now we conclude that F is continuous with respect to subspace A union B with related to topology. Now by the given assumption, this F can be extended. Now by the given assumption F can can be extended to whole space, that is, f is given from A union B to A B, defined by f of x A if x belongs to A and B if x belongs to B. This f can be extended to whole space. Now this f can be extended to whole space by the given assumption f from x to A B, such that f of x is equal to f of x for all x belong to A union B. Or you can write it f of x is A if x belongs to A and B if x belongs to B. Or you can write f of A is A and f of B is equal to B. Now xt is normal by Urichsen lemma. What is Urichsen lemma? A topological space xt is normal if and only if for every pair of disjoint closed subsets A and B of X, there exists a continuous map, say G, from X to a closed interval AB, such that G of A is equal to A or G of B is equal to B. Hence xt is normal. Now this we have proved the if part. Now we come to its second part, only if part. Now we come to only if converse part. For this proving converse part, what is given here? First, let xt be normal, be a normal space, and A be a closed subset of X, and F be a continuous mapping from a closed set A to AB, be a continuous map. Now we show that this continuous map F. Now we show that the continuous map F extends to F full space. That is, value of F at A is equal to value of F at A. Now we have given X to be normal space, A be closed subset of X, and F be a continuous map from A to closed interval AB. This is given, and we have to prove that this continuous map can be extended full space. Now to prove this, we have to build. Now for our numerical purposes, we replace closed interval AB by minus 1 to 1. For numerical calculation, this closed interval and these are homomorphic. Now, to prove this part, we have to build up a sequence of functions. We have to build up a sequence of functions f n g n and sequence of closed subsets a n b n. This is the sequence of continuous functions on a. This is sequence of continuous function on x. A and b are disjoint closed subset on a, and further is closed subsets of x. So a and b are disjoint closed subset of x. Now for this, let us consider first, let us consider f naught is equal to f, where f is a continuous map from a closed set A to -1 to NA. Now for scaling, this is minus, this is 1, this is -1, this is 1 by 3, and this is minus 1 by 3. That f naught is equal to a. Now define a naught. What is a naught? A naught is equal to f naught inverse f. F naught is equal to f. It is a continuous map, and this will be the part minus 1 by -1 to -1 by 3, and f naught is continuous, and this is closed interval. Its inverse image is also closed because f naught is continuous, so a naught is closed. Now b naught, this is f naught, and we take upper part 1 by 3 and 1. F naught is continuous, inverse image of a closed set is closed, so b naught is closed. A naught and b naught are closed subset of a, and closed, in fact they are disjoint closed subset of a, and further is closed subset of x, so a naught and b naught are disjoint closed subsets of x. Now define a map G naught from x to -1 by 3 to 1 by 3. How we define? Now use the result to define this map. Now how we construct this? Let us see. We will use here the result. Let xt be a topological space and A be a closed subset of x, closed subset of x. Assume f is a continuous map from f a to -k to k. Then there exists a continuous map G from x to -k by 3 to k by 3, such that g of x minus f of x is less than 2k by 3 for all x belong to A. This is the result. Now we consider the map G naught from x to -1, 3 to 1 by 3. Now also using Eureson lemma. What does Eureson lemma state? A topological space xt is normal if and only if for every pair of disjoint closed subsets A and B of X, there exists a continuous map F from A to 0, 1 such that from x to 0, 1 such that f of A is equal to 0 and f of B is equal to 1. This is now using the previous result and this lemma, we will find G naught A naught, this is equal to minus 1 by 3 G naught B naught, this is equal to 1 by 3. Now define now G naught, this is now consider a map. This map is continuous. Now using those results, we consider a continuous map. In fact, a continuous map G naught from X to S defined by this. Now define a map F1 F naught, define a map F1 by F1 is equal to F naught minus G naught. F naught is continuous, G naught is continuous, this is so F1 is continuous. Now this F1 is continuous on A. Now F1x, this is less than equal to F naught minus G naught, and this is less than equal to this portion comes out from here, this portion comes out from here, and we have left 2 by 3. 1 minus 1 by 3, 2 by 3. Now F is a map from this to this, and G, in fact G is a map, continuous map from X to minus 1 to 1, satisfying the condition I already. So this G naught is continuous on A also, F naught is continuous on A also, F naught minus G naught is continuous on A, so F1 is continuous on A. Now this first step is complete. Now we come to the second step. Now we have left how much mapping? Now from the scale we see, now we have left F1. Now F1, that is here, F1 is a mapping from A to minus 2 by 3, 2 by 3, this one, and this is 2 by 3, and this is minus 2 by 3. Now what we have done? We have to remove upper 1/3, lower 1/3. Now we take here 1 by 3 into 2 by 3, and we take here minus 1 by 3 into 2 by 3, and now we form, define A1, this is equal to, now F1 is continuous map, F1 inverse minus 2 by 3 minus 1 by 3 into 2 by 3, or you can write also here x is such that F1 of x, this is less than equal to minus my 1 by 3 into my 2 by 3. This you can write also. Now define V1, this is equal to F1 inverse. You can take here 1 by 3 into 2 by 3, comma 2 by 3. You can write here x is such that f1x, and this is greater than equal to 1 by 3 into my 2 by 3. Now we see from here these are closed set and f1 is continuous, the inverse image is closed, so this is closed subset of A and it is again closed subset of X, and similarly this is f1 is continuous, f inverse the continuous image of a closed set is closed, so this is closed subset of A and A is closed subset of X, so A1 and B1 are disjoint closed subset of A and X. Now by using a result as we have stated earlier, result and Eurasian lemma, we define a continuous map. Result is that X be topological space, A be closed subset of X. Assume that F is a continuous mapping from A to minus K to K, then there exists a continuous map G from whole space X to minus K by 3, it reduced to range 1 by 3, such that G of X minus my F of X is less than equal to 2 by 3 K for all X belongs to A. X is topological space, A be closed subset of X, F is a continuous map from A to minus K to K, then there exists a continuous map G from X to minus K by 3 such that G of X minus F of X less than equal to 3 by K for all X belong to A. Now using this result and the Eurasian lemma, we define a continuous map from X to, from here to here. Now we define it continuous map minus 1 by 3 into 2 by 3, comma 1 by 3 to 2 by 3, and define G1A1, this is equal to, this is G1A1 is equal to minus 1 by 3 into 2 by 3, and G1B1, this is equal to 1 by 3 into 2 by 3. Now F2 is equal to F1 minus G1, and this is equal to F0. This is F1 is equal to F0 minus G0 minus G1, and this is equal to F0 minus G0 plus G1, and you see from here F2x is less than equal to F0x minus G0x plus G1x, and this comes out to be equal to, we have to remove this portion from here, we have removed this portion from here. Now if you subtract 2 by 3 minus 2 by 9, and it will comes out to be 6 minus 2, this will comes out to be 2 by 3 whole square. Now G1 is a mapping from X to minus 1 by 3 to 2 by 3, 1 by 3, 2 by 3, and F2 the mapping comes out to be 2 by 3 ka square. Now, continuing in this way, at the end stage, we obtained, before that, we discussed second stage. In brief, this is 1 by 3, this is minus 1 by 3, this is 1 by 3 into 2 by 3, and minus 1 by 3 into 2 by 3. Now, at the second stage, we obtained A1 is equal to F1 inverse 1 minus 1 by 3, comma minus 1 by 3 into 2 by 3. And this can also be written as x is such that f of 1 of x, and this is always less than equal to minus 1 by 3 into 2 by 3. And b1, this will be f1 inverse 1 by 3 into 2 by 3, comma 1 by 3, and we will obtain this. This is can be written as x is such that f1 of x is greater than equal to 1 by 3 into 2 by 3. This is. Now A1, B1 are closed subset of A is closed subset of X, so A1, B1 are disjoint closed subset of X. Now consider the map G1. G1, the map is considered by using this result. Consider the continuous map. XT with topological space, AB closed subset of X. Assume that F is a continuous map, F from A to minus K to K. Then there exists a continuous map G from X to, then this range goes to 1 by 3, such that F of X minus G of X is less than equal to 2 by 3 K for all X belong to A. Using this result and using Euler lemma, we consider the map G1. Now Euler lemma states that XT is a topological space. A topological space, XT is normal if and only for every pair of disjoint closed subset A and B of X there exists a continuous map F from, or you can say G from X to AB. You can write AB also, you can write 0, 1, such that G of A is equal to A and G of B is equal to B. The topological space XT is normal if and only for a pair of disjoint closed subset A and B of X there exists a continuous map G from X to AB such that G of A is equal to A and G of B is equal to B. Using this result, we consider the continuous map. Consider the map G1 from X to minus 1 by 3 into 2 by 3 to 1 by 3 into 2 by 3, and define F2. We have defined F2. F2 is equal to, this is equal to F1 minus G1, and F1 is equal to F0 minus G0, and this is, we place the value F0 minus G0 minus G1, and this will come out to be F2 minus G0 plus G1. Now we write the nth stage here. Now G1 is a mapping. This mapping G1 is mapping from here to here. This range is continuous, and this is F1 mapping. Now define and nth stage AN. We write AN. Now AN, this is equal to Fn inverse minus 1 by 3 minus 1 by 3 is to 2 3 power n, and this can be also written as x is such that f1 of x is less than equal to minus 1 by 3 into 2 by 3 power n. Now similarly we write bn. This bn can be written as fn inverse 1 by 3 into my 2 by 3 की power n and 1 by 3. And this can be also written as x is such that fn of x and fn of x, and this is greater than equal to 1 by 3 into my 2 by 3 की power n. This is an and this is bn. Now bn is equal to fn inverse 1 by 3 into 2 by 3 power n comma 1 by 3, and this is can be written as x is such that fn x greater than equal to 1 by 3 into 2 by 3 by n. Now this an and bn are also disjoint closed subset of a, and a is closed subset of x, so a and bn are disjoint closed subset of x. Now we define using this, we have already stated the result. We defined gn. Now gn is equal to f of n minus में f of n minus में g naught plus में g1 plus में so on plus में gn minus 1. Now we conclude that now f of n is the mapping from a to minus में 2 by 3 की power n and 2 by 3 की power n, and gn is the mapping from x to 1 by 3 minus में 2 by 3 की power n comma 1 by 3 into में 2 by 3 की power n. In this way, we obtain affinity sequence of continuous mapping defined on the closed subset A of x, and it is closed subset of x, and G is continuous mapping on A, on x. G is continuous mapping on x. Now consider the series. For each x belongs to x, summation n 0 to infinity gnx. Since gn of x is less than equal to 1 by 3 is 2 to the power 3n. Since this is bounded, so this series is bounded. Since this is less than 1, therefore the series summation n 0 to infinity gnx is bounded. Why? Now summation n 0 to infinity g1 of x, this is less than equal to summation n 0 to infinity gn of x, and this is less than equal to 1 by 3 into 2 by 3 की power n, and this is equal to 1, and this belongs to closed interval minus 1 to 1. Now by viscous approximation test, now by viscous approximation M test on uniform convergence. What is a viscous approximation test? A series of functions summation n f n x converges uniformly in a closed interval, AB if there exists a positive convergent series Mn, say of numbers such that fn of x less than equal to m of n for all n belong to n and x belongs to AB. Now by using this viscous approximation test, the series summation n0 to infinity g and x converges uniformly to a continuous function, uniformly to a continuous function, f. Now unit converges to uniform continuous function f. Now we show this f map is the extension of f. Now we show f is the extension of the map f. In fact, this is continuous. Now Gn of x, this is equal to f naught x minus summation I0 to n minus 1 Gn x. Proceeding limit n tend to infinity, proceeding limit as n tend to infinity. We know Gn of x is less than equal to 1 by 3 to a 3 power n, and Fn of x is less than equal to 2 by 3 to power n. As n tend to infinity, this tends to 0 and this tends to f by Weierstrass approximation test. So this comes to, as proceeding element tend to infinity, this comes to 0, this is equal to f naught x is equal to fx, and this is equal to minus f of x, and this implies f naught x is equal to f of x. Hence this shows that this f is a continuous extension of f. That is, we can write that value of f at a is equal to value of f at a. This completes the proof of the theorem.